We have some new grad students in the audience, so thanks for coming. So before we get started, I just wanted to let everybody know we're doing a very new type of show. We're actually, what we're calling a hybrid show is going to happen tonight. So we have one of our very own new grad students, Marz, is going to be giving a talk via Zoom, which is going to be streamed up here. We should be able to hear everything, communicate, everything like that. So please bear with us if there are any technical difficulties. The reason we're doing this is so we can have a much broader audience of speakers come in and give talks. So if you were watching our virtual shows last year, we had some really cool people from all over the country give talks. So we wanted to extend that and try and bring that in, which is why we're doing a new type of talk today. We also have Allie, our very own Allie Crisp, is going to also be giving a talk in person after Marz as well. So with that, just a few reminders, we do have our tip war. So our tip war this month is going to be which is better, terrestrial planets versus gas planets. So we'll be bringing those jars around, or you can visit our merch table. If you haven't already, please get a ticket. We do have a raffle going on. The raffle will be announced at the end of the show. So make sure you hold on to that ticket. If you haven't got one, go see Kayla all the way at the entrance. And with that, after Marz's talk, we will have question and answer, but if you do have a question in the audience, we have a microphone over here. So I will ask that you go to that microphone and speak into that microphone to ask your question. That way our online audience and our online presenter can hear you. And with that, we have Marz, and we'll go ahead and give it up for them.
And hear me okay, but I'm sure we'll troubleshoot as the show goes on. If not, so I can go ahead and share my screen. Let's see. Oh, I need to have access to the screen share. All right. Okay, so hi, I'm Marz, and I'm a first-year grad student at LSU starting this fall. And for the past 3 years, I've been working with Dr. Matthew Penny on tracking asteroids. So today I'm going to tell you some more about these minor planets that make up our solar system. So when we say minor planet, what are we talking about exactly? Well, they are objects that orbit around stars, but more specifically, they mainly fall into two groups, which are asteroids and dwarf planets. Asteroids are made up of metal or rock. They don't have an atmosphere because they're too small, and that can distinguish them from most planets or dwarf planets. And they're also considered to be remnants from the solar system formation. And I have a picture at the bottom here which shows one of these young solar systems forming planets. The dark rings are where a planet would be forming, and it's clearing its orbit as it goes around the protostar at the center. And then the red blurs, which make up the rest of the image, would be where groups of planetesimals would be. And any of these leftover planetesimals that don't get fused into a planet would come to be known as asteroids. Dwarf planets are similar to asteroids in that they don't have a clear orbit. They may have more elliptical orbits that cross over another planet's path, like how Pluto crosses Neptune's orbit. And the thing that separates them from asteroids is that they are large enough to have a pretty round shape, or as round as possible. So you can see in my picture on the right here that Ceres is much more spherical than a lot of these other objects. And this is what would classify Ceres as a dwarf planet rather than an asteroid. So we can find asteroids all over our solar system and even beyond our solar system. But within our solar system, we have asteroids that can get a little close for comfort, what we call the near-Earth asteroids. But we also have the main belt asteroids and what are called Trojans. Trojans share an orbit with a planet because they've been trapped in a Lagrange point that is either leading or tailing the larger planet. And Jupiter has the most Trojan asteroids, which is probably because of its mass, but also because of its proximity to the asteroid belt, because the asteroid belt is between Mars and Jupiter. And even Earth has 2 Trojan asteroids, even though we're one of the inner planets and we're not as big as Jupiter. We still have one Trojan asteroid that's leading our orbit and one that's tailing us. The farthest minor planets that we know of are beyond Neptune in what's called the Kuiper Belt, but we also have the rare opportunity to see objects from other solar systems that visit us. And I'll talk about this more in a later slide. First, I'll talk about the nearest objects we can find in the main asteroid belt. So the asteroid belt is found between Mars and Jupiter, like I said, and it contains the majority of asteroids that we know of in our solar system. It's hard to picture on a 2-dimensional map that I have in this right corner here, but the belt is more of a donut shape called a torus, which is shown at the bottom. And something else that's surprising after seeing shows like The Magic School Bus, where a spaceship has to dodge and weave between incoming asteroids, is that the average distance between asteroids is actually about 600,000 miles. So you don't really need to worry about your spaceship if you plan on going to the outer planets. You probably wouldn't even notice that you were in the asteroid belt. Within the belt, there are some asteroid families that tend to share orbital properties, but overall, there's just a wide range of asteroids found that have a variety of sizes and materials making them up. Now we can talk about the more nerve-wracking minor planets, the near-Earth asteroids. There are several different kinds, including the Apollos and Atens, and many Atens are potentially hazardous, meaning that they come within 0.05 AU of Earth's orbit and are big enough to do some damage. Now, these asteroids that cross the Earth's path would be problematic if they cross the Earth's path just when we happen to be there. So we want to keep a close eye on these Earth crossers. But we also have Amors and Atiras. Amors stay on the outside of Earth's orbit, so this little blue circle here, and then Atiras orbit completely within the Earth's orbit. So they always remain between the Earth and the Sun, and that's not shown in this image, but so it would just be right around the Sun in an orbit that's smaller than the Earth's. In addition to the main asteroid belt, we also have the Kuiper Belt, which is found beyond Neptune's orbit. A lot of asteroids can be found here, but also most dwarf planets are found in the Kuiper Belt. It's generally harder to discover objects in the Kuiper Belt simply because of the distance and how dim these objects are when observed from Earth. But we also get visitors from other solar systems, and the first interstellar object that we observed was called a Muammua, and this was a cigar-shaped object, and that's shown in this picture at the bottom. And it had a path that was deemed too eccentric to be bound by the sun's gravity. So we know that comets have really eccentric orbits, and that's because they originate from what's called the Oort cloud, which is even farther than the Kuiper Belt. And this orbit was just even more eccentric than the comet's orbits. So we knew that it had to come from outside of the solar system. So there are over 1 million asteroids that we know of so far, but there was a time that we knew almost nothing about asteroids. So here I have a video that shows the asteroid discoveries over time, and hopefully this also works out. So we start out with like very few objects being discovered per year, and those show up as little white dots, and then they turn into green. So most of these asteroids will be green because they're not Earth crossers or near Earth. They would be in the main asteroid belt. And then notice how as Earth orbits the sun, the asteroid discoveries tend to follow Earth. This is because we're making our observations from the Earth, of course. And then later on in the 1990s, let's see, there tend to be a lot more asteroid discoveries just because sky surveys began in the 1990s. So this gave us the ability to find a lot more asteroids in a shorter period of time. So you can see the discoveries really starting to build up here. And then I'm just going to skip to the end where you can see that there are a great number of asteroids that we've discovered, and it almost looks like a solid circle. But yeah, if you compare that to what we knew in the beginning, we've made a lot of progress. And there are still millions of asteroids to be discovered out there. So the first minor planet discovered was actually Ceres, and at the time it was said to be an asteroid, but has been reclassified as a dwarf planet because of its round shape, because it has a great enough mass to be able to form that spherical shape. Ceres happens to be the only dwarf planet located within Neptune's orbit, and it's in the main asteroid belt. It also has these interesting little shiny spots on its surface, and those are thought to be some sort of brine, and it just makes it really cool to look at. And I think, yeah, this is one of the most interesting minor planets to look at in the solar system. And another interesting one is Ericoth, because it's a contact binary, meaning that it formed from two separate asteroids. And so the diagram at the bottom sort of shows how these two asteroids became locked in an orbit with each other and eventually grew closer and closer and closer until they just fused together to become one asteroid. And the last minor planet that I want to go into detail on is the asteroid Bennu, which has been the subject of a few news stories because we visited asteroid Bennu with the OSIRIS-REx mission. And so OSIRIS-REx was to tag the surface of the asteroid instead of landing on it. So just tag the surface, collect samples, and then it would return. So we expected the asteroid to be fairly solid because even though Bennu is basically just a collection of gravel, it's being held together by cohesion. So think of one of those videos of an astronaut playing with a sphere of water on the International Space Station. Those spheres of water are held together by cohesion, just like Bennu is. But when the probe tried to take a sample using a small puff of air, the surface of the asteroid reacted very, very strongly, suggesting that the surface was not as stable as we thought. So that moment is captured in this GIF on the left here. And you can see there's a very strong reaction, and that was entirely unexpected. So this is where I'm going to talk about my research a little bit. How do we find all of these asteroids? I sometimes get asked about the movie Don't Look Up. So the image on the left is actually a screenshot from that movie, and I thought it would be interesting to sort of compare it to a screenshot from my own work, which is shown on the right. Now, Jennifer Lawrence had it pretty easy because she was looking at the comet. She was looking at a comet instead of like an asteroid, which has a tail, so it makes it recognizable. And probably with a little help from movie magic, you can see the comet very, very easily on that very dense background of stars. In the image on the right, however, it'd be very difficult to find a small, dim moving object in all this mess. So what do we do? How do we find an asteroid in that? Our solution is to take an image that is used as a reference image and compare that to images taken throughout the night. So the difference between each pixel value in the images creates another image called a difference image. And these are very helpful because they do a great job of showing changes between the images over time, such as variable stars, which change in brightness, or an object in motion like an asteroid. I can load the difference images into 3 different color channels, red, green, and blue, which highlights the motion of the asteroid. So the red, blue, and green dots on these images show an asteroid at different times in the night. And after I track the asteroid over a whole night, so these are some of the tracks that I have, after I track the asteroid, then I can plot its positions, and I use those positions to submit them as potential discoveries to the Minor Planet Center. So after all that, you might be wondering, should I be worried about an asteroid blowing up Earth? We know that something of that nature has already happened in the past. The Chicxulub crater is accepted to be the impact site for the asteroid that killed the dinosaurs. That asteroid was probably about 10 kilometers in diameter. There are plenty of asteroids that size in the asteroid belt, so maybe it's worth a moment of reflection that the plot of Don't Look Up could become a reality in many ways. However, I feel that we've never been more prepared to deal with an asteroid impact than we have now. So there are multiple sky surveys that add to our list of known asteroids that are currently active. That's Pan-STARRS, the Catalina Sky Survey, and NEOWISE. And even amateur astronomers can make discoveries and increase the odds that we'll see an asteroid long before it becomes a problem. And NASA's JPL also has 2 systems that are set up to monitor the orbits of potentially hazardous asteroids. So even ones that are not officially discovered yet can be monitored by the SCOUT system. And as long as we keep funding science and space exploration, scientists can keep doing their work of keeping Earth safe. And if anybody tries to convince you not to look up at a big comet coming to hit the Earth, don't listen to them. And that's all I have for you today, and I'll be happy to take any questions.
All right. So, like I said before, if you guys have any questions in the audience, feel free to go to that microphone over there, or you can actually come up here to the stage and ask the question. And if we do have a question online, so Marz, your first question is, how dense are asteroids?
I have a good answer to this, but I will say that there's a wide variety of the types of materials that make up asteroids, and the asteroid Bennu, for example, is just a collection of rubble. So it really varies. I don't think I have a very good answer for that, unfortunately.
Well, thank you. We do have another question. We have, how large is an AU?
An AU is the distance that Earth is from the sun. So we use that to measure distances in the solar system just to make it easier than saying millions of miles.
Awesome. Okay, and we definitely have some questions coming in online. So when you make the different images in color, are you applying the colors of the filters, or are the colors representing the times?
Colors are representing the times. So the red, blue, and green are 3 different images at 3 different times, and I put them together to show how the asteroid moves.
Awesome. Okay. How much data science and algorithm math do you have to know to be able to correctly take in, understand, and study the data you collect?
I would say that a good deal of coding is involved. Of course, there is a bit of math involved too. Like, you do need to know different functions, like quadratic functions, sine functions. Those are really helpful in fitting the various orbits or paths that the asteroids take. So, definitely knowledge of functions, and coding is a big must. I use Python and also Bash in my research, and basically knowledge of solar system dynamics, like how orbits work, things of that nature. I wouldn't say it's too much math because I personally am not a huge fan, so it's not too much for me. So that's got to say something.
Awesome. Are there any questions from the audience? Okay, going once. We do have a question. They're coming up to the mic.
What is your favorite movie where the Earth is attacked by an asteroid?
I haven't seen too many. Unfortunately, I think the only one I've seen is Don't Look Up, but I know that's a comet, so I don't think it counts, but it's the only one I have.
Aaron, did you have a question?
Yes, I do. That was a great talk, by the way. Thank you very much. When you were doing your research, did you find that there was one specific filter that was preferential in finding these things, or did it not matter?
I've done all of my research with asteroid tracks using red filter, so I haven't been able to compare the different filters we used. I've just been using the red filter, and that's mostly because it was recommended to me by my advisor. So I would say the red is probably the best.
Awesome. Are there any more questions from our audience? Cool. All right. I actually do have a question. It is our AOT tradition of what is your favorite Pokemon? All right. Thank you so much, Marz, for the great talk. If everybody can give a round of applause. I know you probably can't hear it, but... All right. Thank you so much. We are going to move into our intermission. We do have some trivia for you guys. It is a little bit different than before. It's going to be Who's That Scientist? So we're going to have some volunteers pass out some cards. If you would like to participate, you have until the end of the intermission. Feel free to go grab some food from the Chimes, hit up the bar, and yeah, we should be back in probably about 10, 15 minutes.
about planets, there have been philosophers and scientists theorizing, despite the occasional threats of being burnt at the stake, that there could be other planets out there. To them, it makes perfect sense. Why should we be special in that our star has planets? And so we've theorized that these exoplanets exist, but we didn't have the technology to prove it until the last few decades. But, and I'm kind of getting ahead of myself here if we're going by numbers, but essentially over the past few decades, we have ended up finding them, and we've found a lot of them. And we've found enough that we've been able to classify them. And we kind of, astronomers have this thing where we kind of just classify everything based on what we know about our own solar system, which is like when Marz was explaining what an AU is, that's the distance that we use because it's the reference that we have. So that carries on into exoplanets in that we sort of classify, describe them in terms of our own planets. And we mainly break that up into terrestrial planets, which are rocky, small, kind of like the inner planets in our solar system, Mercury, Venus, Earth, Mars. And the giant planets, which are gas or ice giants like Jupiter, Saturn, Uranus, and Neptune. And beyond that, we can break them down into even smaller subtypes that are not as clearly defined. And that's where you get things like super Earths, which are terrestrial planets that are 2 or 3 or more times the size of Earth, or mini Neptunes that are like Neptune in our system in that they're icy sort of gas giants. They have like more rock than something like Jupiter or Saturn would have, but still they're gas giants. So they're like Neptune, but they're smaller. And then you have the super Jupiters that are primarily hydrogen and helium, except they're even bigger than Jupiter. So if we want to call the first exoplanet discovery our 9th planet, the first obvious choice for that would be 51 Pegasi b, or Dimidium. And that was first sort of announced, discovered by a group from the University of Geneva in 1995. This was led by Michel Mayor and Didier Queloz. And then it was the first exoplanet discovered around a main sequence star. And for that, they were awarded the Nobel Prize in 2019. But you may be wondering, Allie, what's a main sequence star? And I'm glad you asked, because I have a slide for that. So the main sequence star is, well, let me go back. I don't need this. So we call this diagram over here a Hertzsprung-Russell diagram. And that's basically a plot where astronomers take the brightnesses that they have for their stars and then the temperatures that they have from their stars, and they just put them all in one big plot. And that ends up causing this sort of strip right here, which is the main sequence. And you can think of that like the star's adulthood. It's already done forming, so it's not really like a child. It hasn't reached the point where it's starting to get towards stellar death, so it's not really like an old man or anything. And they do have a broad range of characteristics, but it is just sort of like adulthood. You can think about it like, I don't know, I'm 26, people my age, I'm still in school at 26, but then other people have houses and children or on their second divorce and stuff like that. So even though they're all very different, they're all still sort of in this stellar adulthood stage. And that's also where they fuse hydrogen into helium in their cores, and it's where they spend most of their lifetime. And notably, the sun is a main sequence star. And I think to some extent that's kind of why 51 Pegasi b gets this reputation, because we expect main sequence stars to have the planets, so it's a main sequence star with a planet, so it's special, yes. But in any case, it is the first main sequence exoplanet confirmed, and it is what we call a hot Jupiter exoplanet, meaning that it's like our Jupiter, it's a big gas giant planet, except it orbits so close to its host star that it has an orbital period of 10 days or less. And to put that in scale, Mercury, our first planet to the sun, has an orbital period of 88 days. So you can imagine that these are super close to their star and super hot. And so we've found since then that the radius is about 2 times the radius of Jupiter, but mass is only about half the mass, which probably thinking that seems a little suspicious. And maybe it does. It kind of does. But the reason for that is because it's so close to its star, it kind of gets, the atmosphere gets puffed up, and so it looks really big, but it's not very dense. So really, that's fine, it checks out. It's just, it sucks to be a hot Jupiter. But depending on how you define first, there are several other ways that you could define the first exoplanet. 51 Peg isn't really super special, I guess. I mean, it's, like I said, it's the first main sequence, but it's not really always the first, depending on how you classify it. Take, for example, Gamma Cephei AB, also known as Tadmor. The paper announcing it was published in 1988 by Campbell, Walker, and Yang, and if you're keeping track, that's a full 7 years before they announced the discovery of 51 Peg B. But why is this not the one that is considered first? Well, they weren't super confident in the size or the mass that they had gotten for the planet from the radial velocity method, which I will explain in a minute. So they weren't 100% sure that they could say that it was actually a planet and not just a really small star or a failed star that's called a brown dwarf. And so in 1992, they retracted their statement that they had found an exoplanet. But then unfortunately for them, in 2002, they looked again and they were able to confirm it. So it was actually a planet the whole time, and they could have been first, but they decided that they didn't believe in themselves, which there's probably a metaphor there somewhere. But the radial velocity method in which they've discovered a lot of these early exoplanets is best thought of like, if you think about a siren on a police car or an ambulance or whatever driving by you. When it's further away from you, it sounds kind of shrill, and then as it passes by you, it pitches downward. That's because the movement of the vehicle, the ambulance, the police car, whatever, is compressing the sound wave in front of it and then stretching it out behind it. And light is kind of a particle, kind of a wave, but for the purpose of this, we'll just care about the wave part. We don't have enough time to explain wave-particle duality tonight either. So if you think of light just as a wave, it has this same sort of effect as sound waves, and that's called the Doppler effect. And so essentially a movement from a star or whatever that's giving off light can be sort of shifted to the red or shifted to the blue based on how you're looking at it relative to where it is and how it's moving. And so you can see that in the spectrum down here. As the planet here is orbiting the star and sort of shifting it a little, like this is supposed to represent like the motion that the planet is causing on the star. You can see here it shifts the spectrum there. And so if you have enough information, you can take the size of that shift and determine the mass of what's causing it based on how big the shift is. And so if you know the mass, you can then say, okay, well, it's got this mass, so it's not really big enough to be a star, so maybe it's a planet. And that's how a lot of these early exoplanets were found. But getting back to the planet, Gamma Cephei AB, the radius was later found to be 1.12 Jupiter radii, and the mass is a whopping 9.4 times the mass of Jupiter, which is why they were suspicious. Another first could be HD 209458b, which is a mouthful, so we're just going to call it Osiris, which is its other name. Osiris was the first exoplanet to have its mass and radius measured directly, so if you're the sort of person that would only consider it a planet if you have as much information available as possible, this might be your guy. It was also the first exoplanet observed with the transit method. It was first discovered with radial velocity, but then they followed up with transit and saw it transiting as well. And basically the transit method is just when a planet passes in front of a star, it gets dimmer, and then you can tell things about the planet based on that, and you can figure out whether or not it's actually a planet. It's kind of like watching a lunar eclipse, basically. And so it was announced almost simultaneously by two groups in late 1999 and early 2000, and it has a radius of 1.35 Jupiter radii and a mass about 0.71 Jupiter masses. And then this, to me, is my favorite. I think it's probably the real contender for ninth planet. This is a pulsar, pulsar PSR 1257 plus 12. Two of the three planets around it were the first confirmed exoplanets, and they were published about in 1992. But the problem with this is, since it is a pulsar, it's not a main sequence star, people don't necessarily consider it as important as a discovery around a main sequence star. Essentially, what a pulsar is a neutron star, which forms after a star has collapsed from a supernova or there's been a merger or something like that. But it's a neutron star that rotates rapidly and ends up emitting these beams of electromagnetic radiation from its surface that you can see here. And so they saw these two planets and then later found the third one. But they weren't necessarily really expecting that. The thing is, since the pulsars themselves are only formed in these violent situations like supernovae, they sort of assumed that if there were any planets there, they would get destroyed in that process. So they weren't really necessarily looking for planets when they found it. But since then, people that study pulsar planets have decided that maybe they were formed from debris from the supernova after the pulsar was formed, or if it was formed from a merger, it could be formed from the disk debris left from that. So I think it's pretty cool. You may notice that I did not include names for these like I did everyone else. And that is because they have cool names. Since the pulsar is a dead star, they decided that they would name the entire system after dead things. So the star itself is named Lich, and this is, for you World of Warcraft fans out there, if you still exist, this is the Lich King from World of Warcraft. The first planet is Draugr, the second planet is Poltergeist, and the third planet that was discovered later is Phobator. And so what do we know about these? We know that Draugr has a mass of about 0.020 Earth masses, Poltergeist has a mass of about 4.3 Earth masses, and Phobator has a mass of about 3.9 Earth masses. So really, really tiny, you can see, for the first one at least. But you may be wondering, I had radii on all the other ones, so where's the radius on these? That's kind of a product of how they were discovered. Like I said, these are pulsars, pulsar planets. Instead of being observed like with radial velocity or transit or what we consider the more typical ways of discovering exoplanets, they use what is called transit timing variations. Not transit timing, pulsar timing variations. I study transits, so it's a little stuck in my head. So basically, like I said, the pulsars have this pulsation, that's why they're called pulsars, that is very steady. It's so, like the frequency of it is so consistent that if you could harness a pulsar to use in your watch, it would be more accurate than an atomic clock. So if you see any sort of variation in the timing between the pulses, it's usually an indication that there's something else there interfering. And so with that, they were able to take the differences in the timing and conclude that there were planets there. And so that's how those three were found, but we don't have enough information for that method to make a radius estimate. So we only have radii, or we only have masses. So to me, since it was the first that was not retracted, one of these planets should be considered the real ninth planet. And in that case, since Draugr and Poltergeist were the only two of the three that were initially announced, one of those should be the ninth planet. And I don't know how you would decide which one is better. I guess they could rock, paper, scissors for it. But in the grand scheme of things, maybe it doesn't really matter, because at this point, as of yesterday, when I checked the Exoplanet archive to get this number, we're actually up to 5,069 exoplanets confirmed, with thousands more waiting, like in the archives, waiting for someone to look at it and say, yeah, that's definitely a planet. So it doesn't really matter at this point. And if you're keeping count, if you take our 9, our 8 plus whichever, that includes our whichever one we decide is first, that brings us to 5,077 planets. So in the end, it maybe doesn't really matter. I did not mean to make a Linkin Park joke there. Maybe the Pluto argument doesn't matter at this rate either. But in any case, I will take your questions now.
Yeah. Thank you so much, Allie. That was absolutely fantastic. You did great. Another round of applause for Allie. All right, so with this talk, you don't have to come to that mic to ask a question, because we don't need to have our person online hear that. So if anybody in the audience does have questions, now is your time. Yeah.
So I noticed that a couple points throughout your kind of presentation, express like aspects or radii as difference. Planets are sources of the Earth masses and Jupiter masses. Is that because the planets in question were like really gaseous, and those are the ones like standard there?
So question was, why did I express things in units of Jupiter radii, Jupiter masses, Earth radii, Earth masses? Essentially, that's because, like you said, it's kind of the classification for that type of exoplanet. It's the closest sort of analog to that planet most of the time. And so it's easier than saying like, oh, it's 26 bazillion kilograms or whatever. So.
Another question from online, or I guess our first question from online. How common are pulsar planets?
I'm glad I looked up this number. I don't know how common they are in pulsars as a whole, but I do know that we've discovered 29 of them as of yesterday when I checked the archive through pulsar timing. So compared to like planets that we found from transits, that's on the order of thousands. So it's not really that common, but we don't know if that's a limitation of what we can observe with current technology or anything like that. Or maybe they just aren't that common because it takes a really, really special situation to form.
Any more questions from the audience? Ron.
Ron asked why pulsars are so accurate, and I know it has something to do with the magnetic field, but I'm an astronomer, so we ignore those. I still don't know how magnets work.
That's definitely fair. Are there any other questions from the audience? Oh, Tabby.
think the TLDR of that is what was the community response to the type of discoveries? I was not born yet, but my general impression was that they were kind of skeptical at first because that's a big step to take and accept, and so people didn't necessarily want to immediately accept it, but as they got more and more data that indicated that these things were real, it got more acceptance and less, oh, y'all are just crazy alien people.
Yeah, right.
So the question was, is there a simple answer to measuring multiple planets' masses in the radial velocity method? I know that there is a way that they can distinguish them, but I don't know how they do it myself. I think maybe it's, actually I won't even speculate because I don't really know enough, but I don't know if Tabby knows. I guess you do them one at a time. That'll do it. Question was, of those 5,000 exoplanets, how many are considered Earth-like? And I don't know the exact numbers on that. I'm assuming just because most of them are discovered with transits that probably they are super Earths mostly, or mini Neptunes, just because you're going to be able to see a bigger planet with the transit method more easily. But I don't have like an exact, oh yeah, like 2,000 of them are super Earths or anything like that.
Any other questions from the audience? Okay, I actually have 2 questions for you. Which one do you believe is the true 9th planet?
Plus or minus Pluto.
That's fair. That's fair.
If we're not counting Pluto, I'm gonna go with the Lich system just because I think it's fun that half of them are also metal bands.
Perfect. All right. And of course, our last question, our traditional question is, what is your favorite Pokemon?
That question varies from week to week, but right now it's definitely Psyduck because I've had a migraine off and on since Saturday.
All right, thank you so much, Allie. That was a phenomenal talk, and thank you once again. Okay, next we have our trivia results. I know everybody's waiting for that. I know that was a very lovely trivia. We do have Jonas who's going to go over the correct answers, and I'm sure we will get a lot of groans and moans from the audience, so please give it up for Jonas.
Yeah. So, based on the answers, I would say that was quite obvious. That's the guy with the apple. And then it got, so to say at the beginning, you all did a really great job in finding my clues. So yeah, we have a picture of a messy room, but it can become even messier. And that's the name of this French guy, Charles Messier. And he is famous for his nebula, so many of the globular clusters are shorted with an M, and that's for Messier, or Messier. I really like the answer that Charles Dumpster. Yeah. So the next one is Vera Rubin, and so she is famous for the existence of dark matter. So, and I hope you all can see the connection. And that got to these Roman soldiers, so and is for Nancy Grace Roman, the mother of the Hubble telescope. And one of my favorite, mainly because of this little joke down here. So if you look closer, that's Ulm, and that's the city of birth of Albert Einstein. So yeah, to be fair, so I'm from Germany, and you might get, so the German word for A is ein. So it's even closer in German, but bringing it to that guy, so yeah, 1/2 is 1 hertz, and together with the spring or with the symbol for sprung, it's India Herzsprung, so that's a Danish guy. To be fair, most of the famous scientists were born before the 19th century, and they are mainly from Europe. So that was also one of my favorites. That's Hawthorne with a hawberry, and in combination with a king, it's a hawking. And I think you all know Stephen Hawking. Another guy who works with black holes is Carl from the Llamas with Heads, and a black shield, and with the hint translate that to German, it's Schwarzschild, and that's the name of this guy. And coming to this symbol, we have, as in the talk by Ali, the red and blue shift, and that's the Doppler effect. So, and finally, I here really like the answer that's drunk Prince Harry. Now it's William. With a beer. And yeah, some of you really got William, or the German, Austrian version Wilhelm beer. And he is famous for mapping the moon. And that brings me to the end. And you have the winner, which with 6 points.
All right, we actually had like a 5-way tie, so we just kind of did a draw. And our winner is Kayla Nowak. Congratulations, Kayla. So good job, everybody. And thank you, Jonas, for coming up with a very difficult trivia. That was very creative. I was very impressed with that. All right, and our last thing for the night is our raffle. So go ahead and get those raffle tickets out. All righty. All right, I think this is the one. All right, 3, 0, 4, 6, 7, 3. Hey, we have a winner. All right, congratulations. All right. So you're welcome to go visit our merch table, and you can pick out our item of merch. And congratulations. And thank you to everybody who came tonight. And let's give another round of applause for our 2 speakers. All right, and we will see you in September. Keep an eye out on social media for our announcement of our next show, and have a great night. Thank you.